So, I know it is basic.
Yeah,
Professors used to
now we
tell,
can start.
thanks. Professors used to ask us if, please raise your hand if you're absent. Uh, that reminds me. So hi guys, I'm Srijit Mukherjee. I have done my undergrad and graduate studies in statistics from ISI Kolkata. That is where I've learned my basics of mathematics, probability, and statistics. After doing my masters, I decided to statistics. To be very honest, is all mostly about tabular data or very structured data. So I wanted to do more on unstructured data like image, audio, and I realized it is done in engineering field, electrical engineering. So I decided to do my PhD in electrical engineering. It was not an easy journey. I have to learn. I have to take undergraduate classes in computer vision and all these things, which are fun. And I realized that I understood it better because my fundamentals in mathematics and probability and statistics was made good by ISI. So that helped me in that direct way. My current research work is focused on uh, medical imaging AI. I build, so in medical imaging, there are a lot of bad data. Bad data means low quality data. And my work is how to use low quality data to build AI models, like small AI models, small to medium AI models. We cannot build large. And we will see today what large means in this specific case. And yeah, and so I like to teach and share my knowledge so that others can do whatever they enjoy doing with their knowledge. So today's discussion is about large language model. I have been taking giving this talks of large language models for last 2 years. So I have built a course, free course out there on my YouTube, combining all the talks. So I will suggest you to go back and watch that. The reason is that, I mean, you will find a lot of similarity here. Also, this is a 2 day workshop. It's very dense, as you can understand, and I do not expect you to learn everything. But today's discussion, what I want to achieve is I want to put those pockets of ideas in your mind that you can remember so that it can help you in the other classes. And then you can go back, listen, watch these lectures once again, and you can watch detailed mathematical versions of what I'm teaching so that you can get better ideas. So I will refer to all these things like towards the end. Just give me a minute. I have referred to all the learning resources, and I have referred to all the slides from where I've taken the images. So go back. It's a long journey. And after this discussion, if you have any doubts, feel free to reach out to me on email or LinkedIn, and I would love to help you out to learn and help you learn. Okay. So let's get started. So today's topic is large language model. Now we will understand it in a very principled manner. Professors before me, Professor Sharkar, I do not know who else have taught you, probably Professor Mukherjee. So, and I saw that Professor Sharkar has talked about embedding. So I will kind of start from there and talk a bit more about that. So large language models has three words: large, language, and model. So we will first start with language. What does language mean exactly? What is the mathematics of language? And this is where the connection point of Professor Sharkar's talk with me. And then I will add the keyword of model. What is a language model mean? Okay. And there are various examples like a language model is essentially equivalent to next token prediction. And this, whatever transformer you see from 2017 onwards, it has been there for the quite a few decades out before that. How people used to do that. I will take one example called ngram. Okay. And then I will go to neural language models where people started to use neural networks for language. I will not discuss much about that, but I will just talk mostly about attention and transformers because of in the interest of time. Um, but I will refer you to videos of Stanford engineering where they have discussed RNN in detail, so you can watch them, build an entire foundation of that later on. But yeah. So next is I will discuss, then I will add the keyword of large. That what does large mean? And Professor Sharkar has already touched upon that. He has mentioned the term pre-training. The thing is that since it's large, we cannot learn it in a small way. We cannot just train it. We have to do it in a very specific, very optimized, very sweet manner. And we will discuss that. And then the question is that how do I achieve the business needs of that? So all this self-supervised learning, pre-training, and then um, the supervised fine-tuning, SFT, then parameter efficient tuning, all these things come naturally out there. These are core concepts that you need to understand, or at least remember, so that you can go ahead and like the thought process should be clear in your mind. And that's my, I will believe this lecture will provide enough insight if you can remember the story, the thought process that the whole thing has been built. So let's start. So first question, what is language? To understand what is language in the context of language modeling, you have to understand what is the definition of language modeling. So language modeling is specifically defined, let's be very clear, is given a sequence of words, what is the next word? For example, like you can see we already are using that. And whenever you type something, the next word comes up. How does it do that? So we are trying to build that. Okay. We are trying to understand how does it do that. So next, we'll come back to the basic question that what is language? So language has two components. One is a semantic, that is a meaning component. Language has some meaning, right? And there's a positional component. Now let's understand that by a basic simple example. Let's say Srijit loves to dash, and I have some examples here. Okay, so let's see which one provides semantic meaning information, which one provides positional information. So let's say barking. Sure, barking. Understand that barking has neither has semantic meaning because I am a human being. I cannot bark, and neither and cannot be positional because after two and becoming full stop, it cannot be barking. Do you see the point? So it neither has positional information, neither has semantic information because it doesn't align with Srijit or a human being. Swim. So observe that swim and swim both has positional information and semantic information. A human being can swim, Srijit can swim, and it is perfectly fits in this position. Okay. The next, play cricket, same. Think deeply, same. Do math, same. But coding, no, because it has no positional information but just semantic information. Like if it was code, then it would have been fine. But since it's coding, its position it's not clear. Okay, so semantic information is there. Um, so eating deer, I mean, uh, this has positional okay, but semantic it's not okay because I'm a human being. Okay, and of course similarly the position is fine to lay eggs, but since I'm a human being, I'm a mammal, I cannot do that. So therefore it has two information. As you can see, all the combinations are there. It has two information: semantic, the meaning, and the position. All of you clear about that, guys? Can I get a thumbs up?
Yes, Rajat.
Superb. Okay, perfect. Next, so one important thing about image is that about language is very different. I will discuss that again. Is that if you take any other unstructured data like image, you will see that image is much more local information. Like you can see something locally, but language has a global context. Okay. For example, let's take this word. Like it's a long context length. So it has, for example, take this word, Harrington or sentence. Harrington taught at Harvard University and the National War College. Now understand, Harrington has a relationship with National War College. He also has a relationship with Harvard. And this National War College is towards the end and Harrington is towards the other end. So there's a long, you can write a big sentence, very big sentence, and still the two tokens or two words can have relationship, even if it's at a far end. So that's why position is very important. Okay, and we will see why RNN or convolution or recurrent structure cannot solve this problem. And attention came at the right specific spot and hit the right spot. And that's why you could solve this problem. So tokens or words or has two essentially two things, two meanings, semantic and position information. I'm repeating this over and over again so that it is staying in your mind. It's the concept I need to remember for the next session. Okay. So now to answer the question, what is language? We need to also understand the components of language. So first, so when we say understand human, first of all, understand language doesn't exist in nature. It is a human-made thing. Okay, because our brain has a much more advanced brain. We built system of language, symbols, abstract thinking. Okay, to communicate ideas, right? So that's why it's a built up knowledge for communication of human beings. Also, that's why it's important. So it starts with a set of symbols, a collection of symbols. Understand when you saw A, B, C, D, I mean, or any word before you learned a language, you had no understanding. It's just symbols, some characters. So it's a collection of symbols, and it's a finite because human brain can think in a finite way. So let's call that collection of symbols as vocabulary. Okay. So the fundamental question is this: that what will be the element of those language? Should we take it in? What are the foundational atoms of those language symbols? Should we take it as a characters A, B, C, D, or words for our processing? So there are multiple ways to do that. But what works, and already Professor Shorkar has talked about that. But for purpose of teaching, okay, someone talked about byte like BPE, right? Byte pair encoding, and that's a way to do that for sure. But I do not think it's an efficient way. I do not know who follow Andre Karpati, but he also said like I actually learned from him. So I'm just paraphrasing him that it. I mean, when you break up a word, it actually loses its meanings in some sense. Like if you have the word token and you add a few characters up there, the like let's say you have this token, it is a single word. Let's say this word token is a token, but if you add the certain characters, it will break up. Let's say token then n dot dot dot. So it changes the meaning, right? So but when you have a large amount of data, it works well. But when you have a large amount of data, but you do it on a very specific cases, sub cases, which doesn't occur much, it will fail terribly. It because it's all about how many times it has occurred one, and we will see why is that so. It has roots in something called n-gram modeling. Okay, so we have vocabulary, so the collection of all symbols, and then this question is important: what is the optimal pair of tokens? And this has been answered by the researchers, but in this specific case, today's exposition, we will only consider words, okay, because it has semantic meaning and position both. And again, the question is how are xi semantically related? That's another question. And positional information. So how it is done, as already Professor Shorkar has discussed, each word or each token is represents as a vector. Now, why a vector? Because understand, we want to first of all do math, and we want to represent this mathematical object, and vectors are the simplest mathematical object. Why not a single real number and a multidimensional vector? Because it is a multidimensional thing. You already have two-dimensional aspect, semantic and position. There can be multidimensional relationship, right? Like um like take any word, okay, like Srijit, it has multidimensional relationship with human being and also the emotions and also math, right? It's multidimensional. We want to understand the relationship. So what we do is that we represent the multidimensional object so that it can capture multidimensional relationships. That's important. Okay, that's why it's a vector in RDA, not a single number. um, Positional information, that is the one to how it's positionally encoded, and the semantic information. The semantic information is we define semantic information or relationship as how many times, like the relationship, pairwise relationship, Srijit and love, okay, Srijit and math. This pairwise relationship we mentioned, we are trying to understand. And what is currently done now is, so if you observe this, we can represent mathematically this pairwise relationship in a matrix format. Okay, and we will say this matrix is nothing but the attention matrix, what we will see later on. Okay, so this is the core fundamental you need to know about language, guys. Okay, any questions out here, or all good? Can you
Could
give
you
a thumbs
please
up for
explain
Bhumika?
why this word
Yeah,
called attention metrics? Why suddenly this word
I
came
will
in as
come to
an
that.
attention?
Yeah, I will come to that. The simple answer is that every word is attending to every other word. That's why
Got
it's
it.
attention.
Got it. Got it. Okay.
So, Srijit, you mean to say for any kind of specific language like made by human, so you have this position, semantic, questions, as well as my vocabulary. These are the four components, right?
No, no. Question is what I meant is that we need to answer this question. So three components: vocabulary, semantic, and position. I said
Hmm.
question is what are the optimum choice of this vocabulary? Like, should I do it character wise? Should I do if I do character wise for English language, it will be A, B, C, D, E, F, G, H, 27 Z letters, 26 letters, sorry, and then also the full stop, punctuation, and all these things. If you do it word wise, it will be much more because now you're taking collections. So which is optimum? For example, OpenAI used to use or probably right now use 1 lakh 10 to 100K such tokens. Okay.
Right.
So what is the
Hmm.
optimum way to do that? So you have to do, it's an experimentation problem. Yes.
Yeah.
Is it
So
clear?
apparently, yeah. Apparently, I would like to understand from you, like how this language can capture the emotions or like ethical emotions. Is any kind of
Language cannot capture that. First of all, we do not know, okay, we do not have a mathematical definition of emotions, right? Emotions exist relative to other emotions. So what they're trying to solve is they are trying to have a positional and semantic information to connect those, like as I said, single, like I mean, love doesn't exist singularly. Love exists because hate exists. Okay, or other
yeah,
emotions
yeah,
exist. So what
yeah.
I'm saying is that they have no singular value meaning. They exist
Me.
together. They exist. So that's why relative. And when they're relative, position matters and the connection, how much they're relative, that matters. And using your question, I will go on to the next idea is that how do we measure the relationship? How do we measure that which one are closer, which one are far away? Like,
The conditional probability you were saying.
yes, in this case, cosine similarity, conditional probability will come later on. But yes,
Okay.
conditional probability has something to do with, yes, you're right. I will talk about that. So when I say, we have already said that we can represent these tokens as vectors, but the question is that how do we make sure that two are related to each other? The relationship that we capture by something called cosine similarity. Okay, it's kind of, if there are two vectors, we can,
Okay.
it's the cos of the angle between that, because the
Yeah.
cos, yes,
Okay. Just carry on.
yeah, because if you have cos, if you have like if it's an obtuse angle, if it's far away, that will be negative. If it's close, it will be positive, if you remember the cosine graph, right? uh okay, I will come back to this again later on, yes. But yeah, cosine law, cosine, I don't think it's cosine law, sorry, cosine law is in triangle geometry. I wrote it wrong. So, but cosine similarity, this cos of theta is how we measure the similarity, closeness of two vectors. Okay, and I already, so the thing is that I've already discussed that, I will just revise it. I am giving the slides because I have detailed, mathematically dense lectures on this so that you can instantly connect when you go to my YouTube channel and watch those videos that, oh, okay, he's talking about this. So tensors are the basic of mathematics. In images, we use these pixels to understand those. We have vectors. When you have two-dimensional, it's called matrix. When you have multi-dimensional, it's called tensor. And this is what we do when we deal and code in PyTorch. Okay, all these are tensors. Okay, it's a multi-dimensional vector, you can say. So language is a tensor. Again, I will repeat this in a different way. Is that we have to calculate. So I will repeat this with the language perspective more. That statistical and distributional semantics. Statistical semantics is more about positional encoding. Okay, how these are all words from things from uh, how what language linguistic people have said, and distributional semantics are regular like words, which is nothing but our meaning. Now, one more important thing about distributional semantics is the idea that king minus man plus woman. That means your removing the identity of manness from the kingness and adding the womanness. So the kingness version of womanness is nothing but the queenness. So that's why queen should be ideal. So what I did is that I took the bird tokenizer, I took the token out there, I took the embedding, and I got the embedding of this. I wanted to see if it's working or not. Okay, I wanted to see that, and I took the embedding of that, and you can see that king minus man plus woman. Of the first thing is coming out to be king. Okay, that's where things get fun because it's a vector we started with. Okay, it's a vector we started with. That's why it's coming, and it's just not just for here. It's for all the other tokens. So that's why it's coming out to be mostly related to that. And since that's why the whoever has plus in front of them, that also comes. That's why woman also comes later on. Okay, minus doesn't come because it doesn't have much similarity. But queen comes in the second place. So queen appears in the top list. So that's why it tells you that it is actually doing what we are thinking it's doing. Okay. So all of you got this, guys? So this is how we capture. We want to build the vectors in such a way they have this relationship. And when we are learning using this large language models, it's turning out when we are pre-training it, it's turning out that in fact they're learning it. From that, we are understanding that it has actually learned the language. Okay. Can you give a thumbs up if you're okay with this, guys? Because we're going to the next topic. Any questions?
Srijit, can you explain that king and queen part through vector? What just
Yes. So
here? Yes.
so what I'm saying is that king minus
Yeah,
queen is
this
same
one.
as man minus woman.
Right. Right.
If you think in terms of set, the what king and queen has in common is this royalness, right? So when you
Uh,
subtract
yes.
king minus
Yes.
queen, the royalness gets subtracted. So the difference is nothing but equivalent to a man minus woman, right?
Yes. So
So we want to capture this.
king minus man should be you're the owner of the land or owner of the empire, and plus women
King minus man is royalness, you can
royalness.
say.
Yes. Yes. Yes.
Royalness.
Yes.
Like, I mean, what I'm saying is that the things you need to do to go from a man to a king is the same thing you need to do to go from a woman to queen.
Got
So,
it.
at least in the semantic sense. Some questions, some words are missing.
Like I think some
Oh,
audio problem. So
I'm so sorry.
certainly some words are getting dropped.
Ours
So
is cracking, sir, actually.
yeah.
I'm so sorry. I didn't know that. Please let me know if you do not understand something. Please
No,
stop
no.
me.
So we could follow that. So we could add those misses as such. But yeah, but
Okay.
it's happening.
Yeah, I have no control over it. So,
Yeah,
but
then
I will
please carry
try.
on. Yeah. Instead of losing time, you can continue. Hopefully we can make it.
Yeah.
Yeah.
So we have understood probably what is the essence of language. So all of you got the essence of language. To remind you, we have a vocabulary, we have a semantic meaning, we have a positional meaning. Each vocabulary consists of tokens, fundamental atoms of language, which are represented by vectors. Positional is nothing but we want to understand the position, and then semantic information, that pairwise relationship between tokens. Okay. This is all about language, guys. So now the next question comes is, what is a language model? Okay. So language model, as I have defined already, that we it's nothing but the task of predicting the next word. Like the students open there, it can be many things, right? So what is the mathematics of that? So the mathematics of that is that you can think it. I will come to this and again go back to this slide. So first we have started with vocabulary, right? A set of tokens, fundamental atoms. So what we're trying to do is that every word you see, imagine this, like many of you probably are investing in stock market, right? So let me draw a connection. Since stock market, every point is a random, is a distribution. You do not know where it will go or not, right? Every point, whatever you're investing, is random. So what you do, you fix a probability distribution on that. That's how whole the financial quantitative finance people do. They fix a probability distribution on that. Okay, that's what they call stochastic process, Brownian motion. Similarly, here, language is same. exactly similar to stock market. Every point in stock market, it's a real value, okay? But in this case, it's, so let's say you have a word, okay? Next word. This is a random variable. We do not know what the word can be. I mean, already it has multiple choice, and this actually motivates probability distribution. This is an experiment, and you can have multiple observations, multiple outcome of the experiment. Like if you close your eyes and pick and see whatever sentence you have, like the students open there and see all such sentences where you see the phrase students open there and see the next word, that's a random variable. You're randomly picking out from a choice of what from the choice of, you're randomly picking out from the choice of, tell me, what are the choices? What is the outcome space?
Choice of words only, right? So
One word, any word that would
The
fit
available
the
data,
semantic as the
What
efficient
is the name of that?
the language, the
semantic
training
word.
What is the name of that?
vocabulary.
name of what?
Exactly. So the vocabulary is the set of outcome space. So every word can take values as is the probability distribution over the vocabulary. So it's the outcome space on which we are building a probability distribution. Okay. So we are building the stock market analysis like this. Like here, every word is a distribution over the vocabulary, and we're trying to understand the distribution. But here it's a bit more, to be very honest, the whole system, like if you now do after learning this, if you go ahead and do a deep learning for time series, the same training process and everything will be the same because the mathematical framework is the same. So the problem is, given a sequence of words, okay, what is the probability of the next word? Okay, just like we can say, okay, the past few days the Tesla stock or the Google stock has done this, has got these values, the closing and opening price are this, what will be the closing price next day? Similarly here, though, if the word is, let's say, the students open their observations, what will be the next word? Similarly, so the probability of x of t plus 1 given the past t words is what we are trying to find. All of you understood this, guys? Any question? And every xt plus 1 is in this vocabulary. Okay. So this is what we define as the next word prediction problem. So language model is nothing but this next word prediction problem. Understand this probability of the next token given the past tokens is nothing but a function of the previous tokens, right? Like for example, I do not know about time series modeling, but financial modeling, I mean about your knowledge. But what I'm saying is that if you know something like Arima, I don't know. Like you have many business problems, like auto-regressive models. Actually also that's why language model is called auto-regressive models.
yes,
Okay. So if there's
yes,
some
yes.
ARIMA things, AR model, right? In those who are business analysts or those who predict stock, like sales growth or something, autoregressive models are there, right? So similarly, it's an autoregressive process. You're using the past k minus 1 data to predict it. Okay, so how many days you take in the stock market prediction? It's nothing but same thing here, which is called context length. How much context you're taking here. How many past word data you're taking? It's nothing but the context. Okay. So the goal is this f is nothing but a function of this past data based on which you are predicting the probability distribution of tk, because it's a random variable over the vocabularies. And what should this f contain? This function should contain and learn the semantics and positional information. That's very important. Okay, this is new in language, which was not there in time series or other thing, because it is language based. It's a language domain. Okay, so I will not do this much, but yeah, let's not do this much. It will just because I have to explain it. But there is a chain rule of probability. I would suggest you to go and watch the Stanford lectures. I have given 2 Stanford lectures. Please watch them towards the end, and it will like you probably need to devote 3 months or 1 month at least to watch this, understand them, solve the problems. They have exercises and understand, do this math out there. Okay, this chain rule is very important for understanding. Uh, I will not discuss this, but this is basic mathematical setup. Okay, so the next part of what is in what is a language model, you have to understand the simplest language model model existing there that existed before. That is the n-gram modeling. So Piyush is asking, can we relate to the fixed point method used in approximation theory? Are you talking about the recursion, the xn minus 1 to xn? Are you talking about that? How we use xn minus 1 to xn? Like how we update the iteration? I mean, not really, Piyush, but again, these are nothing but a data structures and algorithms aspect. What I mean is that we all use iterative methods to do this. Okay. So what you are saying about the fixed point method for approximation, it's an iterative method. Similarly, every algorithm here is an iterative method. Deep learning essentially it's an iterative process, but it doesn't have direct connection. But glad you observed some connection. But yeah, got it, Piyush? Okay. Okay. So n-gram modeling. So let's take the simple. So I coded this out for you guys. So let's take the simplest vocabulary possible. Okay, that is two characters A and B. So we take the two characters vocabulary A and B. These are the tokens, let's say, because understand in your case A and B are replaced by words or whatever tokens you decide. So this is what I will ask you to do at home if you know coding, is that do this exercise for you and you will understand most of it. Like first take the vocabulary A and B, two tokens. The first 1-gram model is nothing but it's just counting. So do not look at the code. First of all, I was told not to do coding, but nowadays coding is just equivalent language. So I will just tell you what it does. So first we count the number of such characters. The 1-gram model is that we are not looking into any relationship. We are just looking what each characters come out to be. And you can see that A has, since I have generated randomly, A has come out to be 50%, 49%, B has come out to 51%. But in usual case, if you remember, if you actually plot the distribution of all the letters, you will see it actually follows a distribution like this, which is called Zipf's law. It's a power distribution like this. In fact, any counting has a power distribution. If you count Virat Kohli's runs, you will see a power distribution like this. If you count the number of electrons, you will see a power distribution like this. Okay. If you count the number of CTRs on your website, counts on your website, it will be a power distribution. So count has a power distribution kind of value. Okay, it's a distributional thing. Yeah, power distribution, Poincare distribution, like that. But again, it's kind of Zipf's law. But in this case, what I'm saying is that it's just you're not really looking into 1-gram is not, you're not looking into individual tokens. Again, the whole goal is what? The whole goal is this, finding the distribution of this, all the tokens together. So in this case, since they have no relationship, we are saying that they're all independent. So probability of this ABA, this token, or rather probability of A coming after AB is nothing but probability of A, because is nothing but probability of, because you are not dependent on the past. That's why it's 1-gram. Does it make sense? So you're not depending on the past, whatever has happened. Okay. So that is 1-gram. Now what is 2-gram? 2-gram is that you're just considering the pairwise relationship. Okay. So what I do is here I take the pairs and count how many times it happens. Okay. And you can see AA came out to be 0.24. These are all, these are all random. So all of them will be 25% because two options for the first choice, two options for the second choice. Basic combinatorics, basic counting. So 4 times. So 4 options are there. AA, AB, BA, BB, right? So both all of them are similar to 0.25%. Okay. But what I'm saying is that we are now counting pairwise things. This is the modeling now. So the thing is that the whole idea of n-gram modeling is finding this joint distribution or this probability distributions. So this is what the basic n-gram modeling is about. Okay. And then when you find this probability distributions, when you let's say what you define is that probability of A given B is nothing but you count how many times. Okay, let's understand this carefully. How do we count probability of A given B in this case? It's very simple. Probability of A given B is nothing but probability of A and B divided by probability of B, right? So you count how many times A and B has occurred together. That is 0.25, right? Or that is 0.25 into total number of options. So 0.25, how many times probability of B has occurred? So what you do, you see probability of, like, you just do the same thing before like this. Okay, how many times? So it's 0.51, and from that you can find out probability of A given B. But whole idea is to find these joint distributions together so that you can model this, find this. So the whole idea is what? The whole idea is that you are said that A, B, B, A, B, B has come. What is the, so the whole idea is next language modeling is that we want to predict what's next. So the next can be either A or B, right? So that's a vocabulary. So we have to find, since 2 gram, what we are taking is that we are just taking the last one. In 1 gram, we didn't take anything. Okay. In 2 words, we are just taking what is the probability of A given B, what is the probability of B given B. This is what the language model is in this case, right? When it's 3 gram, when it's n gram, you take BB. What is the probability of A given BB? What is the probability of B given BB? When it's 4 gram, you take ABB. Okay, this is how you do it. So now how do you count? I have already told you. You counted, let's say, this probability of A or whatever, probability of ABBA by probability of ABB. You just count how many times it has occurred and divide it by that. Simple n-gram modeling. Okay. So this is a basic idea. So I already told you that what I just showed you, it's mathematically written here. We just count how many times it has occurred together. Okay. Just count how many times it's occurred together, and we just divide by that. And I wrote an example of that, basic dictionary stuff. So you can see that total is nothing but the conditional tokens, that what has occurred beforehand, plus A, because that's the only future possible, because vocabulary is A and B, and similarly conditional tokens like previous tokens plus B, that's the total number. For given text A is nothing but just A part divided by total and B part divided by total. Simple stuff. But here if it was A, B, C, then there would have been an addition of C here. Another one, distribution conditional tokens plus C. Okay, because again it's a probability distribution, and you can see it's just 50-50 here. Fun stuff. So this is all about n-gram modeling, guys. Did you understand? Any questions? Can you give a thumbs up if you have any questions? Bayesian classification. There's no classification here, Anindita. Yeah, you can say unsupervised learning if you want to be very precise. You can say we are learning the distribution of that. You can talk about mixture modeling. You can talk about how the distributions are. We're trying to learn the distributions, but there's no classification here. Make sense, Anindita? Okay, any questions, guys? Okay. So, yeah, it's the simplest model. You're right. It's the simplest possible model that is possible. That's why I'm discussing this. What I'm saying is that it's language modeling has been there for a long, long time. Okay. But one question I have for you guys. Yes.
Can we call these grams are basically kind of lags in case of time series modeling?
Yes. Absolutely, you're right. So that's why in stochastic time series modeling, we also have the exact n-gram version of that. If you consider it discrete, let's say there's a simple project you can do. If the stock market grows up, you call it up. If it goes down, let's say more than 0.1%.
How many times up? How many times
down,
up and how many times? Yeah, kind of.
Yeah, exactly. So if you do that, you can exactly transform that into the n-gram model. It will exactly mathematically equivalent to the n-gram model, and that's how it's done.
Okay.
So you can do this. Actually, it's just 1-to-1. The thing is that in time series, it's a real number. Like the random variable is real valued. Here, it's a discrete value. Yeah. Yeah. But if you observe, yes. Yeah. Okay. So n-gram collocate. Sorry, what do you mean by collocate?
Co-location, I think.
Collocate. Um, yeah, so exactly, yes. They look, yeah, so they collocate a pair of words, you're right. But not just pairs, that's for 2 gram. If it's in 3 gram, it will be 3 words together or 3 tokens together. It's co-location, exactly. And thanks, Indrani, for bringing this up. Why? Because will be my next question, that what do you think is missing, or what do you think is actually done in n-gram modeling that is missing from the actual language we have learned? In language, there was a vocabulary, and out of that, semantic and position information. So what do you think n-gram is doing the one really good, but missing out on something? What are this? What is it doing? Context good or meaning semantic good, missing out on position, or it is doing position good, missing out on semantic? Which one it is doing, or doing both?
Probably it is not looking into the position, because when you look into the sequence given, when we try to predict something given that the previous occurrence, you're only considering the occurrence of frequency. We are considering maybe that we are missing the significance of a particular position of operator. Maybe.
Very good. Yes, it's mostly focusing on position, but you have to also understand that position has some meaning. Like position also leads to some meaning. I mean, the very fact that, so I would say 80% position, 20% meaning, because position also leads to meaning. Like 2 words, if they're as Indrani has said, co-located nearby, it has chance of having closure meaning. So it leads to that, but not always, because as we have seen before, that language can have long dependencies. Harrington and National War College. But taught, this word is mostly related to human beings. So it will be like human being vector is like this. So you will get Harrington vector like this and taught vector like this. So this should be close by. So position has some semantic information, but it doesn't specifically, it's just relative semantic. Okay. Okay. Very good. Again, the math of this is very simple. Not simple. I mean, it's not simple to do in time. So you can again watch the Stanford lectures, but whatever I've taught, that will be enough to understand the mathematics part if you know conditional probability. This is just an example of what I said, okay, with real words. So instead of this A and B, if you just put real words, it will look like this. Okay, this position, it's for 2 gram. This counts the number of times it has occurred together. Okay, and from that you can generate the count. From that you can generate the probability distribution. Okay, so read this up. This is an exercise for you. Read this up. You will understand since I have discussed about this. Okay, so the next question is that how do you evaluate a language model? And this is important. You evaluate language. How do you evaluate the performance of a language model? You evaluate the performance of a language model by something called perplexity. So what is perplexity? Understand this very carefully. If you are predicting a token of words, let's say you're predicting n test tokens, next n words. If you know the probability, if you're really sure about the probabilities, right? If you do not know it, if the language model is trained well and you realize you do not know well, that means your probability will be less, right? Yes or no? Right? So if you have high probability, that means you know it well.
Sir, can you please repeat?
Yes. So what I'm saying is that if you want to predict n words in a test set, naturally there's a data distribution. All of you know about machine learning. No need to go in that. So we want to evaluate the performance of a language model on a test data set, and we have n words in a test data set, n words. How do you define the performance of it? If you know if you know with high probability these words are going to come, the probability of the WIs. Like, let's say this is A, B, B, A. Okay, this is what is in the test data set. Let's take an example. A, B, B, A, dot, 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 B. This is a test data set. So you look at probability of A, what the model is predicting, given the past. Okay, then probability of B given the past. Exactly. So if the model well trained, it's accurately going to predict, and hence the probability will be high. Now we want to understand, when we're evaluating a model, we want something like loss, like we want it to be low. So what we do, we inverse it. If the probability high, we want a low score, so we inverse it. So we take 1 by probability of all of them together, and then whole to the power 1 by n to normalize it. Because it will be too small, right? So we normalize it to make it bigger. It's like a kind of geometric mean, you can say. So it's like product of like geometric mean. All of you know what geometric mean, right? Product of n numbers whole to the power 1 by n. So it will be product of all these probability of predictions. If you express this in this conditional probability form, it will be nothing but this is the each word prediction problem, because it's a given. That's why this calculus is important, because we are trying to model in this, but this is nothing but the product of n next word predictions. That's the whole language modeling is all about. So it's a product of that. So we want to essentially find the geometric mean of all the predictions on each of those words. Does it make sense, guys? Simple, right? It's a like geometric mean, or like inverse of the geometric mean. Because why inverse? Because if the geometric mean, if the model is well trained, it will be high probability, right? High probability of success of predicting a word character correctly. We want we want a measure that gives low score when it's really good. So we do 1 by of that. So it's an inverse or 1 by the geometric mean of all the probability of predictions given the past data. Make sense, guys? Can I give a thumbs up? If not, ask me questions. You have any questions?
I have one question. We know there is a measurement of uncertainty called entropy in probability distribution. How? What is the difference between perplexity and entropy?
You can see, as that's the next slide, that they're actually related to each other.
Okay.
For example, they are exponential of that. It's like a
Oh.
bijective function of that.
All right. Okay. Okay. Understood. Thank you.
So the probability of that product big number is basically less than 1, and we are taking the inverse and geometry mean to get a integer number. What to relate?
No, geometric mean is to normalize that. Like if you have too much probabilities, it will be less. So you do 1 by n of that, inverse of that, to increase the value of the number.
Oh, Srijit, why do we normalize it? Sorry, I was not able to completely understand that part.
Like if you have n words, okay, let's say you have 100 words in a test data set, and you have 10 words in a test data set. Okay,
Right.
if you have 100 words, the probability will be really less, because it's multiple numbers of probabilities, right?
Right.
Multiple less numbers, because epsilon to the power n goes to 0. So as you have more words in a test data set, it will be going to 0.
Yep.
So what I'm saying is it should be normalized with respect to the number of length. And the good normalization, since it's a product here, it's a geometric mean. Make sense?
Okay. So basically, what happens is if the model is very big and we are testing on a very large data set, so every time it will be 0. So in order to prevent that, we are normalizing it. Is that what I?
Any mean normalization is due to that.
Okay.
Now, in this case, exactly, to prevent that, absolutely.
One question that, hello?
Yeah.
The thing is that does this perplexity is actually related to the English word perplex, because perplex is
Sorry?
meaning that is this perplexity is being motivated from the English word perplexed, that means being confused. So the perplexity
I mean, you can say that, but I mean, probably I don't know that. Actually, I do not
I mean, just
But
the
yeah, probably
intuition
you're
that
right.
is just an intuition, maybe.
Sure, it can be true actually. I do not know, and probably that's why the company's name is Perplexity. But
Yeah, I think
I also sometimes
lower confusion is better uncertainty. That way we can interpret, I think.
you can say that.
Yeah, as well as in entropy
Very
also, that lower entropy is more information content. So
yes,
in that way also we can.
absolutely. Exactly. So lower perplexity is more information content, but I really do not know because actually I have faced this kind of situations. I previously used to think that why it's the meaning, but later I discovered that some word is related to some favorite word of some author. That's why the person gave it. So I've stopped looking into these reasons, but that's a good thing to look. But yes, probably it's perplexity is due to that. But I didn't look into it. Thank you for letting me know. Motivation demand. So Piyush, that's a very good question. So often what you happen, Piyush, like um, before you let the model into the before Piyush, Shomo, did you understand Shomo or you have a space?
Yeah, I
More
did,
questions?
but I think I'll have to do some self-study. I mean, I got the idea, but so yeah, thanks.
Okay, so I mean, is there anything I can help you out with, or you want me to explain more, or I can move on to the next question?
No, let's move on to the next question.
Okay, perfect. So Piyush, the defining perplexity is that so often when we want to really before we release a model into the public or for people to use, we want to have some good measures, like simple measures, just like let's like you measure a nation's health by GDP, right? Similarly, by indices in economics, these indices are very important to understand various like for poverty there is an index for specific for several things there are indices singular numbers because human beings are not multidimensional. We are very low dimensional creatures, understand this. We're very very low dimensional. So to understand this we need low dimensional numbers, single number, mostly 99% of the cases. So we want to come up with a single number that can say the goodness of the behavior, and that's where the evaluation metrics come. Okay, so this is just an evaluation metric which is a single dimensional number. You can of course look and see, of course it's good, but but how do you know that it may be just good on the examples you can give, but not on a large scale of examples. So for a large scale of examples, we want to have a singular measure when you combine and average them out, and that's what evaluation metric is all about. Make sense, Piyush? Any questions more? Okay, so next, now we will come to neural networks. And I will discuss a bit about attention here. And understand, before the attention didn't come like this. Okay, attention came after a lot of research, after the recurrent neural networks, after LSTM, all these things, attention came. And I am not discussing that, but you should learn that how it happens, why it's important, and I will talk about why those don't work. Okay, but I'm not talking about that because that's not in the current uh, use right now. You can learn that from the Stanford lectures I have referred towards the end. Please learn from that. But this course will really help you to understand what they are teaching really well quickly. So what is attention? And the question, the most important thing is how does attention solve the distributional semantics? That is the semantic information. And how does attention solve the positional information, statistical semantics? Let's understand that. So first, as I said, the every token has an initial vector. Every token has an initial vector. And people were asking questions to Professor Sharkar. I was listening to them. So initially they were randomly selected. They have a lookup table. So if you do code in PyTorch, it will be nothing but nn dot embedding. This is nothing but based on indices, and there will be an index. Okay. So you have the vocabulary. Let's say the word I is in the index of 5th position. So it will be randomly picking, it is a lookup saved up table. It will randomly picking up the embedding saved in that lookup table. Okay. And then it will train it. Now, why training is important, you will understand this reason, this. So first, when you club all of them together, it becomes a matrix. So this is a d dimension, each individual, this is the number of words n dimensional. Okay. And then you create the key, query, and value vectors or representations. So this 4-dimension reduced to 3-dimension for each one of them. Now, what are we doing here? What is the meaning of that? Let me explain that. The meaning is very simple. Let's say you have a search bar, and you're searching something. I am ... right? So this is nothing but you are querying something. So what do we want to learn? We want to learn that how they relate to each other. So what I'm saying is that when I'm querying, that's the query representation. The key, I am trying to understand. So what I'm doing is that each of these tokens, I'm looking at first the relationship between them. So I represent them as query, and the key is what the outcome is coming or what is saved inside. And you want to map them together like pairwise mapping. Okay, and what we do attention. Okay, so what we're doing is we take every vector. If two vectors are there, x and y, x transpose y is nothing but the dot product of that two vectors, right? You must be knowing that. Now I will connect back to cosine similarity. If you have the dot product of these two vectors, dot product is nothing but what? Cos theta times the length of two vectors, right? So it's nothing but, the dot product is nothing but, you can go back and do the math, is nothing but scaled, it's scaled, and but the most important thing is that how much they are close together. How much the two vectors, the two embeddings, I and love, are close together. It checks here in each one of them. How each one of the words, how they do that, they have a query embedding, they transfer into query part and a key part. Okay, and then see how they are. So, okay, it's not here, sorry. It's the embeddings, new embeddings. So it transforms the embeddings. Sorry, I did a mistake here. These are the new embeddings. So you may ask that why it is the need to do this. Well, first of all, understand that this is the engineering aspect, that they're trying to learn new representations. That's the whole idea. So they are putting wherever they can this small learnable layers so that they can learn by the data, wherever they can learn. So these are the new vectors, and they want to capture the binary pairwise cos theta, the cosine similarity of the two vectors. Why? Because to learn the semantics. And for each one of the pairs, you have 3 words here. So 3 cross 3, 9 words, 9 elements in this matrix, and you can represent this as a pairwise. For example, 0.8 tells the relationship between love and love. I and love is the relationship is 0.7. So it's kind of proportional here. Understand this. It's kind of proportional here. Proportional, but it's, you can say in essence it's capturing this. In essence, it's capturing the cos theta, the relationship. That's what they want to capture, the relationship. The relationship is captured, right? Now the question is that the relationship is captured. Initially, I was here and love was perpendicular to that. Now we know that I and love should come closer. So how do we update that? We have the relationship here. How do we update that? That's why we have the value embedding. We want these vectors to be updated like this, close by, because they have semantically closure now. So what do we do now is that we first capture the relationship Q, K transpose. This normalization happens for stability and stuff. Let's not go into details. If you want to know these details, I have the lectures of this full mathematics, 2 hours just on this attention and transformers in my YouTube channel. You can go that and check, but today is not the day to do the entire math. Today is the day to get the intuition. So we have the attention here, attention score here, which tells a relationship. But we want this relationship to come back into the vector embeddings. So what do? We multiply this relationship times the vectors, times the new vector embeddings to get the new context aware embeddings, which is now aware of the context. and love close by, love and tennis, and I and tennis are close by, right? So this is what the attention attention mechanism is trying to do. First, it's trying to find the key query and find the relationship. Why key query? Because they're trying to find updated embeddings of that, updated representations of that, and they have a value to update the value, okay, based on the relationship. So it's Q, K transpose, softmax. Why softmax? It's nothing but changing a probability distribution. This will take some time to do the math. So go back and check my video. But essentially the idea is this is the relationship and this is the updated vectors. Updated representations which contain the relationship information. That's the most important. The math of this, go and check back. All of you are understood this, guys. This is why attention mechanism solve the distributional semantics.
So
It doesn't solve the position as of now, but it solves the distributional semantics for sure. Okay.
Sujit,
A bit of
in that,
positioning and mostly the semantic. Yeah.
I'm sorry. May
Yeah.
I
Go ahead.
Yeah. In the gray color that box, rectangular box, we can see where actually you define the attention score. There, all the diagonal element has the highest score. Say I with I is highest, love with love is highest, and tennis with tennis is highest. There, actually, it's unlikely that I after another I will come, or love after another love will come. Something else will come. Now, something you are trying to then the at context and the green box. But what are the values? Similar values will come there if we consider numerically.
No. So these are like the attention scores. So it's like kind of saying that from I, it has, so essentially you will transform this softmax, you're transforming this into probability distribution. You will say after I, 25% of going to I, after I, 75% of or 50% of going to love, and another 25% of going to tennis. Okay. And then you have this old value. What you're doing is that you're updating for each one of them, you have this vectors, and you are proportionally adding the vectors using the weights to get the new vectors, which is saying that I have the updated information from these weights.
Oh, okay. Yeah, got it.
Yeah. And yes, Ankita, the question is great. The I and love, first of all, this is an example. I do not know whether, but yes, you're right. The I and love is different from love and I because we're also considering the positional information. Absolutely.
So
Any more
one
questions,
one
guys?
question, Srijit, like this table we are building, this is also based on certain texts already we have, right? Means from the training data we are basically forming this. Is it so?
Yes, from training data, we are finding all of this.
So attention tables and all, metrics and all these
We are
values
trying
also
we are using data to find these relationships and embeddings. Yes.
okay. So we keep on
So
updating
understand that.
this for every iterations.
Yes. So understand this very carefully. This whole relationship is nothing but a function of the tokens. We're trying to find that function. And now we cannot arbitrarily put any function. So what we're trying to do is that we're trying to build a system that encodes the information of the whole domain of the data. Okay, that's why for image, it's a different architecture, convolution, let's say. But for language, it's attention. Make sense?
Yeah.
So the
Okay.
function of the token we're trying to understand. Now, we cannot arbitrarily learn all the functions because it's not possible to optimize. So we are trying to put in structures on the functions that aligns with the data structure. Here, the data structure and data understanding information. And that's why we
Basically,
came up with the attention and then value and key query so that we can first take the relationship and then update the embeddings. Huh? Sorry? Got it?
yeah, I understand. Yeah. So I have
Sujit,
another question in this line.
please
So
go ahead.
sorry. So when the learning or training process is going on, so this attention scores will keep on changing, right? As and when these epochs or the different
When it
iterations
converges
of
with the results, it means that probably it has learned good attention. That's the assumption.
and also this dimension that at the very beginning, how that is determined. Like any sentences can have 10 words, a sentence can have 50 words in it. So how
Dimension of
big
what?
the
The two
attention
dimension.
on the for the first matrix that you had, like the X?
The dimension D, the embedding dimension, the two
Yeah, yeah.
dimensions.
Okay.
The embedding dimensions, it's based on the compute, and it's just experimentation which works. So some people, so essentially all these things, these are hyperparameters. These are all mostly because you can only do so many computer like experimentations, right? So the hyperparameters are usually based on like they did previously, let's say. So there's some background noise. Can the admin mute that person?
I think press
Yeah, the Prasad Chaudhary. Can the admin mute that person, please? Maybe he has mistakenly turned it on. Okay. So yeah, so those are based on experimentations or prior knowledge that it has worked previously, so let's try out with that, and for that it has probably worked. So like that. Make sense?
okay. So it's more like trial and error and figuring out or fine tuning to the perfect value that gives us good results. It's kind of trial and error that we call it.
It's there's and also they see that how many parameters, the other things too, they see how many parameters their model can handle and all these things, and based on that they also like they see that with D how much it increases and decreases like that.
Okay, thank you.
Sure. Yes, so any other questions, guys? Harsh's question I guess is
Shiji,
yes.
so like behind this, what I can understand is once we tokenize our a text after that, like what we are doing, we are trying to prepare the embeddings for it, like the vector embedding. For that, we are using this attention mechanism, which is
Yes.
also solving our distributional semantics, like the relationship between each words. So like my just one concern is like what are these attention heads, like the query weights, key weights, value weights, like what does it basically do? Are they adding weights to these tokens? After that, some attention score correlation is being driven
No,
based on that. We are
so
updating it.
understand, yeah. I also had the same question myself. The idea is that to learn better representations, that's the whole idea. So they are giving space to change it beforehand and then do the attention so that they can save some compute. Like they don't have to do multiple times. So
What
it's
are we
giving
changing?
space to
How are
learn
we
better
changing it?
representations. Yeah, sorry.
How are we changing it? Like the space that we are allowing it, like what is happening
Oh, by
inside the
linear
space?
projection, like linear matrices. So we are changing for 4-dimensional, 3-dimension. So we multiply with the corresponding dimension matching.
Okay, so this is like some feature reduction, dimensionality
Yeah,
reduction that we are trying.
exactly. Yeah.
All right.
And it's learnable because we want the model to learn the better representations. That's it. So it's giving space, multidimensional space to learn it. That's it. That's the whole idea. Make sense?
All right.
Okay. So any more questions? So Kankita is asking, has I answered probability distributions? Probability distributions are these are okay. These are categorical probability distributions. So for categorical probability distributions, it's P1, P2. Multinomial is parametric. This is the parametric, you can say. So yeah, so positional encoding solves in statistical the position part. So in place of initial embedding, it is just not lookup table embedding vectors, but they are also positional information. By positional information, how it is done? It is done by this specific, for each individual position, they have a vector, same vector. Okay, if it's 1, there is a vector. If it's 2, and it's not learnable, it's already fixed. Okay, these are all fixed. And there's some really interesting properties. The recent innovation of positional encoding is rope, rotatory positional encoding, rotation based. The one thing I would like to say, I will not discuss the math of it. It will take, again, go back to the math stuff. But the main thing I would like to say that, look, this is not just random positional encoding. This is selected so that you have the relative position. This function, but a function of I minus j, like position of I of I minus j, like similar to this idea. What it means is that it's if you, even if it's a 2 and 10, it's same as, it's learning the same relationship as 13 and 21. So what I'm saying is that it's learning the relative position really well, trying to learn it. Okay, that's why this specific sinusoidal and cosine, because things are taken so that it learns a relative position, not absolute position. Like it should not be 2 and 10. It should only come at 2 and only come at 10. No, it should be after wherever this love word is, after there's a chance, even if it's the third point or the fifth point, the next is tennis can be coming. Okay, there's a probability of tennis. So we want to learn this relative positioning, and we use sinusoidal and cosine because it has a periodic property. Okay, we can use that. And if you do the mathematics of this, you will see, actually I post this on LinkedIn, you can check my past post. And if you read the paper, there's a line of that, and you should read this new paper called rope, which is enhancing this property. So this is one important aspect of positional encoding. Makes sense, guys? Can you give a thumbs up? Makes sense? Any questions? Any questions, guys? Okay. Finally, so why couldn't convolution and RNN or LSTM couldn't solve this? The RNN and LSTM couldn't solve this because, first of all, in convolution, it's layered by layer, the in size, the filter size, the receptive field, that how each token is connecting to the next token. In region wise, it's slowly increasing. Let's say after 15 layers, or 5 layers, it goes to the entire image. It's not even that. After 18 layers, let's say, it goes to the entire image, and that's a lot of time. So the thing is that, as I said, the language is a global structure. Right away, there is relationship with Harrington and the college, which are towards the end. So we need a right away global relationship which connects every pair of word to every pair of word, which cannot be done by convolution. So it takes a lot of layer and a lot of time, and hence loss of global information, which transformers do, because it, from the beginning only, it is doing the attention. There is pairwise attention of all each words together. That's the best part. It right away from the first layer onwards is doing the global attention, which is a specific property of the language. But in image, often if you do vision transformers, you will see that there is initial layer is a convolution layer, a bit of convolution layer. It helps a lot. In fact, yeah, please read the vision literature also. You will understand how it's different. You will understand the value of language when you understand other domain, because you will see the difference in the minute structures. If you read more papers and ask questions like this, why it is like this, you will see the difference, that how they're attacking vision problems and language problems in a different way. The overall architecture, that, let's say, both transformer is used to vision and language, but when you go minute details, like very minute details, you will see, acha, this is why it's used for vision and this is why it's not used for language. And that is very important for you to build future models. Okay, and also the RNN cannot solve it, or sequential models couldn't solve it much because of the gradients. Similarly, they're gating functions. Okay, you will see gating later on in the mixture of experts if I get time to do that. But in gating functions, there's sigmoid used, and when you again come back and do vanishing gradient methods, when you backpropagate, you have a lot of layers, because you have, let's say, 200 words, or even now, I mean, there are how much? Recently, a model came out with 1 million context length. I forgot which model. So it's a lot of context length. Like imagine there is 1 million layers, and you have like those gradients. It will be going to zero. No learning will be happening. That's why RNN also couldn't work. Like it. So essentially, the whole idea is that the global information, the positional information, it cannot solve. Even though the embedding information was there by deep learning methods, but the positional information it couldn't solve. Ngram solved the positional encoding but couldn't solve the semantic embedding. But deep learning easily solved and learned the semantic information. But it's hard for sequential model like convolutional RNN or convolution for the global kind of model and loss of global information. Like convolution is a local model. So local models like convolution and sequential model like RNN, this cannot capture the global information, the positional information. It's very hard. And that's why attention works. Okay? Makes sense, guys? Did you understand what is a language model? Do you have a better understanding now? So we first learned language model is next word prediction. Then we took an example of n-gram modeling, which is a simple, which solve positional encoding stuff. Then we saw that how attention is solving it. Okay, how attention is solving it, and why convolutions and RNN cannot solve it. Okay, any questions more I can help you out with? Because we are going to the next topic. Okay, so now this is something new, and this is something you will not find in my lectures much. So I will probably take the next 50 minutes to properly address it, to teach it well. So please ask questions. So first of all, the next question, we have understood what is language, what we have understood what is language model, but we need to understand what is largeness. What largeness bring into this language model? Okay, what happens? So yeah, so first of all, what's the problem statement here? You have the input and you have the output. These are input tokens, the output tokens, right? And what we are doing here is that we have this input tokens x1, x2, xn, and we have the output y1, y2, yn like this, right? Just a sequence of token input and sequence of token output. And the function we are trying to learn is this. It's the unknown parameters. We are doing the deep learning process to learn it. So what we do is that given this x1, y1, x2, y2, we have to understand what are the predictions that are happening. Did I not put that? Oh, I have that. What are the predictions happening? What are the output predictions happening? So we will understand what are these x and why it's called self-supervised learning. So in types of learning strategy, let's see how it has evolved. In 2000, there was n-gram modeling. Then the RNN LSTM came. Then the transformers came. Okay, and then all these are pre-training models. All these pre-training models are happening, and all this thing happened. It's a sequential process. So n-gram is not very old. It's 25 years old, n-grams. And RNN and LSTM are 15 years old. So yeah, it's younger than I am. So now types of learning strategy. So this is very important. We already know about supervised learning, where there's an input and well-defined input and output, like image and cat or dog level. Unsupervised learning, like principal component analysis or clustering, where we have only the input, but let's say, yeah, just the input. Okay, no output. We do not know any well-defined problem. So we define a well-defined problem like principal component analysis or clustering. Okay, we define this based on that. There's a reinforcement learning, which is nothing but on a corresponding action, like our interaction between the environment and an agent. Okay, and it has a reward. You want to maximize its reward by its actions. Like it checks that which actions increase its rewards, and it learns kind of a decision tree inside its mind. Then comes supervised, self-supervised learning. Okay, so I will just focus on this. So self-supervised learning is something like language or time series data. So we have no specific, we have only one data set. Like in stock market, we have last 500 years or sorry, 100 years of data, let's say, or 10 years of data. Okay, and we want to understand This is the only data we have. We have no labels. So what we are defining is that out of them, we are defining the labels. So we are creating something called pseudo labels. So what are the pseudo labels here? We will understand that. So pseudo labels here is just the next token prediction. We have a language, we divide it like I love math. So I love is the training and this is the testing. This is the y and this is the x. So we are building pseudo labels. Okay. So this is the self-supervised learning approach. Similarly, if you know 5 days of stock market data, you want to predict where it will go next. So same, we have the entire data, we are dividing into smaller pieces. So all of you understood what is self-supervised learning, guys? In this case, okay. So what is done here is, in this specific large model, we learn the we build such a task to learn the good representations, good embeddings of all the language in a self-supervised pre-training manner. So this helps us understanding which embeddings are good, what are the good embeddings. And then we specifically fine-tune it to specific skills or specific things we want to do. Okay, we will come to that more. So the traditional learning framework is supervised learning, randomly collects X and Y, no pre-training. But now in this modern framework, it's pre-training and pre-training, where we learn this representations and then we fine-tune it. So we have a large-scale data, we pre-train it, get the pre-trained language models like GPT, and then we fine-tune it to downstream task, like specific tasks that we want. Okay, and we have a specific task data set, like we want uh, to build a joke data set. Let's say, I don't know what is this data set about, some data set. Okay, so we want to build a specific fine tune. So we build this and fine tune the model based on that. And there are some issues like this. You will see what are the issues, and that's the whole idea of large language model. Okay. So now pre-training LLMs. So in pre-training LLMs, how the training is done. I will not go into much of mathematics. So there are multiple such architectures using attention and transformers. There are encoded architectures like BERT. There are decoder architectures just like GPT, and there are encoder decoder architecture like T5, right? So there are multiple. So, but right now, what is famous, what is working is a decoder, the GPT style architecture. Okay. So the GPT style architecture is nothing but you input a number of words and you predict the next words. So again, to understand more mathematical aspects of it, please you have to watch other videos. Okay, I have referred to them because I have not taught this as of now in details. So you should watch the Stanford lectures out there. But this is the basic idea. Let's understand it's an abstract concept. We are doing decoder styles only. Okay, it will not change much. It will not change your perspective. So GPT, in 2018, GPT was a big success in this decoder, and it is a huge learning model. The whole idea of large language model is to understand and how to learn such large number of data points. Large with a large model. That's the whole idea. The largeness is the most important thing. In byte pair encoding happens for the tokenizer, and yeah, these are the specifics of that model. Over 7,000 unique books. Yeah. So this is the whole decoder. Yeah. So the whole decoder model of GPT that we are that is being used right now. Again, it's built up of, you can see each transformer block is built up of this multi-head attention, multi-mass attention, and all these things. Again, these are taught in details in my mathematics for transformers video. Do check that out. So these are the data set that is being used, large internet collection of data set. The good thing that happened was before GPT, all this internet was so huge and so much people were creating content. So I believe Google has played a really big role in building the data set, the Google search and all these things, right? So it has all these data sets that they are using to learn it. It's very important to have large, massive amount of data set. For example, this is an example data set. like a random collection of random element, random training sample of the GPT, as you can see. Bizarro Wonder Woman is a Bizarro version of Wonder Woman when Bizarro 3 found himself, whatever. This is a data set, example data set. And what we do again using this tokenizer app, as Professor Shorkar has shown, is we break this up into tokens. Okay, and you can see this tokens doesn't always have meaning. The 11 and TH are not together. Okay, sometimes it has meaning, sometimes it don't have meaning. For example, the Sam E should be idle together because it's single meaning, but it's just Sam and I are broken down together. That's why I do not really like BP. Not my favorite because it's losing the context in some sense. But again, it's a large amount of data. With large amount of data, you can actually do anything. So it doesn't matter actually. So it works for GPT. So it works. But how it is trained? So the idea is that we have this input 4 words, and we build this. As I said, the whole idea is to build a function of these 4 words: T1, T2, T3, T4. The whole idea is to build this function, and this function is approximated by neural network, as I was saying in the beginning, that neural networks can approximate any function if given enough number of parameters. That's the universal approximation theorem. So that's why neural networks are powerful. And out of the neural networks is nothing but we have the vocabulary. So we want a probability distribution over the vocabulary over V. So we have the probability distribution over V, and we get each of the words get a probability. That's what we are predicting. Okay, and whatever has a maximum probability, it gets correct. The answer is, like, let's say this is the highest one. So there are many other ways to do it. Often we take multiple top k and then sample many different ways. That's why it gives different output. But yeah, this is the basic idea of how it's trained. Again, we have this multiple giant parameters. This is a mathematical expression of the function, and we essentially, by gradient descent, we're updating this parameters. We're learning it. The final inference is done like this. Is very important, as someone was asking me. So let's say we have initially one data point. From that we get the probability of which is the best. Let's say we get 860 and we append it to this, and then we input in the neural network this one, and then we see what's the best one, because the conditional distribution, right? We can condition on whatever the best context length is, whatever it has been trained on, and then we get the 287, and then we again input, like, append this, and then we get the next one. Okay, so because we don't have the best, we don't have, it's missing data, right? We don't have the data point. So what we do, we use the best possible prediction out there, and we keep on building one by one. This is how the inference, like when you have GPT. So in this case, like, the meaning of life, first meaning came and then off came. So when you first say I will meet you at the airport, okay, you press airport, and then you use this into you put this I will meet you at the airport into the large language model, and it will give another point, let's say at or full stop, right? So it gives the best word prediction one by one, like this. This is how inference happens. Okay, all of you got it, guys? Any questions? Okay, so next is
Sorry.
in context. Yes.
Yeah, sorry, I had a question there and I was on mute. So I just to give some background, I work in a company, so I'm coming at this from a practitioner's point of view, right? And I don't know if this is the correct place to start her off, but let me take a stab at it. So yeah, that's you showed the model as to how we can now make use of LLMs in our in any place, right? There's a large, or there's a LLM pre-trained with large amount of data, and then we take it and we try to do a fine tuning on it, or we try to do a maybe a continuous pre-training on it, and see if it, or well, put in a rack pipeline or some other form of something, right? So And I will take a real life example of what we are looking at. So we are a software company, right? So we have lots of old software products and lots of old code and things like that. And from there we want to it's still being worked on, and we want to generate code and things like that. And obviously it's not in the public domain, so maybe the pre-training does not have all that data. And I have the model. I have, let's say, Llama, right? I can do a CPT on it. I can do a fine tuning on it.
Yeah.
But none of them are giving good results. Maybe because I do not have enough data for the CPT. Maybe because the problem statements are too complex for fine tuning. Maybe because the REG pipeline is not, or it's giving reasonable amounts of data, but still not good enough for the CPT.
So what is the problem you're trying to solve?
The problem I'm trying to solve is there's a programmer who will come up, give a large description of a coding problem, and it will generate 1,000+ lines of code, or maybe not 1,000+. Let's say 800 to 1,000 lines of code from a pretty descriptive, software problem.
Okay, so you want to explain a software, let's say, in words, in details, and it'll output the code of that.
Correct.
Okay. So first of all, you have to. The first step is.
This is not the place to ask that question, because I understand we're looking at the.
No. So what I will do is that I will take this example and try to connect it to whatever I'm discussing. Okay.
Sure.
So I will answer your question, Dipanjan. Dipanjan, right?
Right. Yes.
Yeah. So first step is you have to understand the language, in this case code, right? So you have to take a pre-trained coding model, like whatever is freely available online. There's a DeepSeek version too, which has a coding understanding, not language. Here human language will not work. Okay, because pre-trained coding is also, it's like a pre-trained version. Yeah. So that's a step number one.
Yeah, and the model I have taken outputs very good code in the same language, if on other problems.
So is it a different language you're working on?
No, it's Go. It's Go.
Okay. Okay. So it's not like you have built the language from scratch.
No. The language is a commonly accepted thing. The LLMs and it's not one. We have actually tried multiple ones. It has very good understanding of Go and spits out very good code. We have tried a few of the techniques that you showed there, right? Whether it's CPT, I don't know. I'm not sure if I saw that. Whether it's fine tuning, but the nature of the beast is. I'm just curious, if this is a place to ask, or if you have seen something like that. And again, I understand I'm coming from a practitioner's viewpoint, a real life case. So,
no, absolutely, you should ask this, and I think this is very important.
Can I take this question?
Absolutely, go ahead.
Actually, my name is Shantanu Karmakar. I'm going to take your NI10 class and the agentic AI class tomorrow. So let me solve or give you some hint how I solve similar problems. What I do mostly, I will show you tomorrow also. Tomorrow I will show you some examples. I tell the LLM my intention, what I am trying to do, and then ask the LLM to generate the prompt. And I don't ask it to generate it one go. Okay. I ask it to generate it in parts. And then it generates almost 16, 17 prompts, one after another. And then I execute them in there is something called OpenAI Codex. I use it for myself. And it generates one after another the entire thing. It is an agent, basically. Okay. It's a coding agent. It takes each prompt, and I keep those prompts in different text files. And then I ask the model to take each of the text file and process. It generates absolutely perfect code in most cases. I'm using Python, by the way. I am not using Go.
Thank you, Professor. I saw your you have those sessions tomorrow, and
Yeah.
I was actually going to bring up my questions.
Yeah. Please. These are very practical questions. I'll try to give you the answers, at least whatever I know and whatever I practice, I'll show you the way. You can try out.
I have put in a RAG pipeline, RAG pipeline in front. I am breaking up the problem into problem things, and I am working with the label agent exactly in the context engineering, or training it in the context thing that is mentioned there. And the results are better than what we got from obviously the training and the tuning, but they're still not there. But I think maybe I should ask it there instead of here. Thank you very much.
Yeah. Please do that. I will show you some, or we can take it up offline also.
Thank you very much.
Some point of time.
Please go ahead.
Yeah.
Perfect.
Go ahead.
Thank you, Professor Kormukar and Dipanjan, for asking the question. It's really very important. The supervised fine tuning doesn't always work, and there are a lot of things you can do. Okay, so when you have a large language model, you have one interesting thing that comes up naturally, that is in context learning, or it automatically learns to do stuff in a simple manner. And also there is scaling laws, that how to optimize the data and the number of parameters. So what I mean by in context learning is you have this, like you give a few examples, which is also called few shot learning. You have these few examples which are coming up more, like you give a few examples and it will give, let's say you get thanks for mercy, hello for bonjour, mean for mente, and it automatically give the meaning for or transformation for outer. Okay, so it's learns for a very few examples that what it has to do, and this is an emerging property of when you train things large, even it happens for vision. There are examples like this. You can read the slides. I'm not going to use this time. One important idea is that the large scale things that happens, and this is something I will explain a bit. So this is called scaling law. What happens is that as you increase the compute, so PF is the perplexity. So in terms of perplexity, as you increase the compute, not PF is not perplexity, sorry. So as you increase the compute and the data size and token, it's an observable trend that the test loss decreases. Okay, but what turns out that the number of the taste loss when you take, so let's now for different total parameters, take the total number of parameters of the model, and based on that you do the test loss, you take the test loss, and you will see that there is a minimum point, and when you take the minimum point, they try to fit on a line, which tells us that the size of training tokens and these parameters, they have a relationship. Okay, they have a linear relationship with each other, and GPT-3 is not optimum for that. The optimum for this is turning out to be this. So this is a 20x relationship. Okay, so again, I would suggest you to watch the Stanford lectures. I don't have much time left. I have to discuss quite a few topics. At least scream through the ideas so that I can put that in your mind. So the whole idea of scaling efficiency is that GPT-3 was performing well, but it was not at the cost. It was using more cost. So the 70 billion parameter model instead of this is working well. And why is it? So there is a scaling law that is happening. So yes, the scaling law has two components. One is it's as you scale, you can find the test loss decreasing. There is a power function formula of that, but also there's an optimal number of parameters, training tokens, and performance relationship where you get the optimum performance, and that happens a certain size. And this can actually tell you that, let's say for a certain number of training tokens, you have this number of data. Okay, let's say you have 100 million data, okay, or tokens, training tokens. Then what is the optimum size for you? You can decide it like before you build the model. You can decide it beforehand, so that essentially it will help you save time. That this optimum number of parameters of the model will work properly. probably I need to train more. So instead of building more parameters, you can train for a longer time. Okay, that can help in better results for sure. Training more epochs is very important. So this is why scaling law is useful, because it helps you to gauge the architecture thing, that what will be the core architectural changes you need to make or reduce or increase to get optimum performance by extrapolating this. This is why scaling law is important for large model stuff. Okay, so now I will talk about this. As I said, the pre-training always doesn't give good results, as Dipanjan was saying also. So supervised fine-tuning is one
Hi,
of these.
I have a question.
Yeah. Go ahead.
Do we for I'm talking about again for continual pre-training. So do we have a direct relationship between the number of data tokens that is required and the number of parameters that should be in the model? Because once the model is pre-trained and once we are going to do a continual pre-train, the number of parameters is going to remain same. So what is there any hard and fast number that this number of tokens will give the best results, something like that?
The scaling laws happens for large number of parameters, but when you say to fine tuning, it usually, for example, if you see OpenAI's fine tuning, okay, they say that even 10 examples work. So if you look into OpenAI's supervised fine tuning, if you just search it, let me see.
Sorry,
I
this is
will just
Dipanjan again. Actually, Shaik was, he's in the same org as me. So this is not the labeled fine tuning though. So we are working on the same problem, right? So the problem is that large, as I said, thing, right? And labeled fine tuning is generally, a question answer, request response, right? So we are talking about the continuous pre-training where we actually try to update the base model itself with our data set, which is not available in the public domain. And we are wondering, I mean, let's say we have a 3 billion or 70 billion parameter model. How much data do we need? And we can take an LLM with open distribution of data, right? And we can put in our coding part and create a data set. But we were
Okay,
just
okay, I see.
curious how much
Yeah, so
data. Yeah.
yeah, I will send you. There's a relationship. I think it's around. There's a number like parameters by data. There's a single constant, probably 20 times or something like that. But I will get back to you. Okay. I
Thank
will
you
send
for
you
it.
also the paper.
Original parameters.
Parameters by training tokens. There's a constant.
So
It would be great.
is that for actual pre-training or is that for continual pre-training? There is a bit of a difference there.
Yeah, sure. So it's also for continual pre-training, but what I'm saying is that you can start trying it over with that. That's a good initial guess. Do you see the point? It's
Sure.
so
Read it
this
properly.
scaling law is for large models,
Sure.
but this constant is for large models. But at least it's a good place to start with. Do you see the point? What I'm saying?
Sure.
I absolutely. And then we do have some trial and error, and we are now very proficient in trial and error because we have tried so many things. But Shahid, can you make that out? Alpha equal to I. Sorry, what was it?
I will send you the paper. Okay.
Thank you very much.
Yeah,
Thank
that's
you.
it.
So what are your names? Mrinmoy and
Mridmoy, Dipanjan, Shayak, you can send any one of us or just.
Okay. I hope you got my email in the morning.
Yeah, we have it.
Okay, then I will get the email from there. Okay. So yes,
I'll
and I
just
will
ping you so that you can
address it.
reply me. Yeah. I'll just.
Sure. So yeah, so there's I think it's a very important problem to ask that for how much parameters I need to add, how many tokens I need, how many training data sets should I add, and I'm sure there is a lot of work on there, and I will send you the relay, at least for the supervised fine-tuning perspective. Now, from the pre-training perspective, when you just give your ask questions or random questions to the pre-trained model without fine-tuning, it gives gibberish answers, right? Like this: explain a moon to a 6-year-old and it will give something about rockets or astronauts, which doesn't make sense. So we want to fine-tune it with the corresponding data set. Okay, pre-trained model doesn't always do that, and for that you have to define the data set really well. And For the tuning purpose, there are multiple tasks you can do, like spam detection, sentiment extraction, um, story writing, list generations, many other things you can do. Okay. Okay, so now in the fine-tuning case, what OpenAI has done is they have done a supervised fine-tuning, and then they have done a reinforcement learning driven human feedback fine-tuning. So I will discuss each one of them, but let me discuss the supervised fine-tuning. So supervised fine-tuning is very important to discuss the training structure. So let's say you have so essentially you should have X and Y, okay, if you're predicting something, and you have a prompt and you have a response. Here's the X and here is the Y. Here is the X and here is the Y. Is the annotation. Now how it is changing. So essentially supervised fine-tuning is very similar to pre-training. You pre-train index exactly in this way, but how you do it in this manner. You have this input ID. So input IDs are nothing but the IDs of the vocabulary. Each token is in the vocabulary. So you take which IDs are there and you mark that this. So you take the entire token, you combine this entire thing into token, all of them together, but you mark that from this point onwards, this is user, this is assistant, this is user, this is assistant. Okay, and you mark the label for that. So that will tell you that this is user, this is assignment, and this is user, this is assistant, this is the training loop, sorry, the data loading loop, the data set building loop. And then you can use this label and input IDs into the model to get the same kind of prediction out there. Okay, this is how the data set is built, this is how the training is done. Yeah, so again, SFT is not different from other pre-training model, just that you have to very well define the problem statement you have in hand. But coming to supervised training, let me just see. Just give me a minute. Let me just see one thing. So I'm sending in the Zoom the OpenAI supervised fine-tuning method. And if you read it in the, oh, did I stop sharing? Or can you still see?
We can
You
see.
can
You can
still
still see.
You can see.
Okay.
Is
So
that
I'm
the
sending
error method
OpenAI's. I'm
yeah,
sending OpenAI's.
we got that as well.
Yeah. So look into that, and you can see that it has said that the minimum number of examples is 10. So build your data set.
The
So
problem
read this.
was this for one of us, Dipanjan Minma Shayok?
Yeah. So
Or
what I'm saying is that yes. Yeah.
okay. No, we have done it. The thing
Okay.
is, supervised fine tuning is with labeled data, right? So it has a
Yes.
question answer or request response pair. Our scripts and code is complex with dozens of libraries spread across hundreds of files. There is no simple way to create. Actually, we have tried to create the data sets for supervised fine tuning. But I think we are at a place where we can say that we have done enough, and it is not possible to create these small simplistic question answer responses for the complex things that we have. So I don't know if you are so the question is something like create 5 tests with 6 configurations of networks doing testing standard stuff from 5 standards. I'm not sure that these are questions where we are not sure. There's a question. Is there any way I can create a supervised labeled fine-tuning data set from there? We have not been able to. And I think the complexity of the original problem statement is the reason. This IFT is great for creating those small bots and things where it's clear, the answer question and answers are clear. We have not been able to achieve a good result.
Yeah.
Also,
So
a point to add. Sorry, this is Vivashu. So most of the data set that we try to even use supervised fine tuning with the OpenAI or let's say Gemini, they actually limit the number of tokens of the data which we can provide. So that's also one of the things which is uh, restricting this particular thing?
Yeah. No, let's understand the fundamental problem. I have not seen a data set, but what I can understand is that you want to achieve something really big, and it's a complex, as you said, right? Um, First, to achieve that, there are two ways to do it. Yeah, one is, if there is no supervision possible, you have to pre-train it just like the way GPT has done it in that large scale, because otherwise it is of no sense, right? Because the whole idea of supervised fine tuning is you assume that the underlying pre-trained model is good enough for your downstream task. Like, pre-training model is 80%, downstream task is 20%. Okay. But if you say that current model is not giving and you have a large complex amount of data set, you have to retrain it in a pre-trained manner, a self-supervised manner. Do you see what I'm saying? Otherwise,
Sorry, please
otherwise
go
it
on.
will be hard.
Yeah,
So
absolutely.
so
And that is where we had these questions. So we have tried that as well, right?
okay.
And we still did not get good enough results. Now we know that Go language is, I mean, you just give it any LLM, give any LLM a question, it does it splendidly, right? And we
Yeah,
have tried,
I think it's right. I can continue with the whole thing. We can take this
yeah,
questions offline.
maybe.
Yeah. So the next, so as I was saying, that supervised fine tuning is good, but it is also very heavy. You can it takes a lot of compute. So we have this thing called parameter efficient fine tuning, where we reduce the number of parameters, because in supervised fine tuning you actually retrain the change the whole model. So what we do here is, in parameter efficient fine tuning, we add adapter networks to the entire pre-trained model, or that's one way, and we build where adapter networks looks like this. We take the output of the multi-attention, it's an embedding matrix, and it not down sample, down project and then up project, and give the same dimension. So it learns, so down project means it learns quality, low dimensional features which are very important, and upscale up project them to the higher dimension for the next layer. So this also really helps. This is less, if parameter, like less number of parameters are needed. This is also one of the things that industry do.
So just wanted to clarify that we don't have the hardware to do a full pre-training, continuous pre-training. We actually use PFT, and we used those LOR, low-rank adapters. So, right? I mean, cost is a big factor. So,
I understand.
Sorry, go ahead.
Yeah. So another thing that we can do is the low rank adaptation. So what we do here is that, essentially, if you see, when you are updating the parameters, this is the old parameters, and the new parameters W1 using recursion is nothing but the old parameters, but plus these new parameters. Okay. So this all new parameters, instead of retraining everything from scratch, what we're trying to do is that, can we find a better representation of these new parameters? And these better representations of the new parameters can be done using this adapter is one of the ways. Another way is this low rank adaptation, where we, instead of this DK parameters, we reduce it down to this low number of parameters, assuming this is low rank. Okay. So if essentially we are representing delta W is B times A. Okay. And you can see the number of parameters is dr plus rk here, which is less than dk here. That's for sure. So r is chosen in that way. So in this way, we reduce the number of parameters by a lot. Uh, so this is how one way it can be done. So yeah, so this is about the parameter efficient. This is how it's, so instead of a matrix, we reduce the dimension of the matrix in rank matrix, and it's also this is also actually important. This is in there in dictionary learning, in core signal processing, where we use low rank tensor approximation, because in many of this whole new tokens, there are a lot of patterns, and the patterns exist in low dimensional space. So that's why, since we already done pre-trained learning, this is very important to utilize. But often the issue is that this leads to domain shift, and whatever you train on, it just gives that kind of output. Okay, because it has low number of parameters. It has no place to explore. So that's why it often is not helpful unless it's for a specific task. Yeah, very specific, well-defined task. Like very specific, well-defined task. That's very important for supervised fine-tuning. So another thing that is RLHF, what they did differently is, um, so what they do, why just they didn't do HF, sorry, SFT, is because the diversity of the interaction may be limited by the content of the training data set. Okay, so what they did is, in step 2, they took a diverse set. They took multiple prompts. They took a diverse set. And this is very important. So what they did is they understood their problem. They put a corresponding prompt to the existing GPTs or large language models and got the output and got multiple such responses. Okay. Instead of creating the data set, they got multiple, like from scratch, they create multiple such responses and got a labeler, a human labeler, to understand or rank them that this is better than this is better than this. And then they use reinforcement learning to um, learn this rewarding, that how to update the model so that we learn this specific characteristics, this specific importance, and how this is a framework, how they have done. Let's say there's a task and they talked with the assistant. This is a discussion, and then they got 2 responses, and out of that they ranked it. This is how the interface looks like. Out of they ranked which one is better, and this is how the data is collected. So they built an interface for that, for the crowd workers. Okay. um, yeah, so I'm not going much into details because this is truly much mathematical, but quite a few things I would like to mention. This is reward modeling. So let's say there is a like reward Ri and Rj for the corresponding responses. Okay, so how do you mathematically model it? So you mathematically model it similar to logistic. So you do the probability y greater than j as sigmoid function of Ri minus Rj, the change in the reward, and this is how you model it. And essentially the idea is that your goal is to learn this reward model so that on the preferences of those pairwise prompts, okay, pairwise data, and you minimize this expected log of the the sigmoid function, the probability of the difference in responses. It's just similar to cross entropy loss kind of thing. Okay, so check it out. You have to, yeah, so okay, so this understanding is really good mathematical foundations for this training and understanding. But the basic idea here is, instead of just supervised fine tuning, they are taking rewards and scoring it in rank and from base to worst. One important thing that happens with RLHF is, often while maximizing rewards, it skews a lot away from the model, okay, from the existing pre-training model. So there's an extra loss of Kullback labeler, which tells you that this reference, the old model and this new model are close together. Okay, and if they are close together, uh, it is good. If it's far away, it's bad. Okay, so minus of minus, it becomes plus. So it's, the more they're close together, it's good, loss is less. The more far away, it's bad. So it's rewarding for lower loss. So this maximizes the reward. One is maximize the rewards, is the parameters updated, and this tells you do not divide away from the loss. So Kullback library is nothing but you get this 2 probability distributions. Okay, and it's telling you that be close together. It's a distance between 2 probability distributions. Yeah, so this is the basic idea. I'm not going much into details again. That's all about it. Okay, final part I believe that is currently useful is the mixture of experts. But again, this is mostly for pre-training. How can you reduce your model? So mixture of experts is essentially, and I will discuss a bit more details for 5 minutes, a bit more mathematically, is you have a large training model. The question is that, let's say I ask you a history or a coding or a mathematics. Now, all the parameters of the model, just like all the parts of the brain, is not involved in every aspect. Similarly, how can we train the model so that we get specific sections activated for specific expert, like history, English, language or grammar, coding, mathematics, medicine, all these experts? How can we build these experts and make the model identify the expert and then take the action? So this is the mixture of experts. So what is done is that, first of all weights are not useful in the forward pass. So these are all engineering things I'm discussing. And the subset of the huge model is only important. So how to identify that? To identify that and reduce that, you have to understand that where the maximum like number of parameters are there, and the maximum number of parameters are there in the linear layers. Okay, so the feed forward network in the transformers. So you can see that how many parameters the feed forward network have. It has 1.115 billion parameters. Yes, probably yes. But it's very large. I have to see if this billions is for billion. So it has so many parameters out there, okay, just for that linear layer. Because it's nothing but there is no structure to it. It's all weights corresponding to all weights. So that's why the whole idea is that, can we reduce this feed-forward network into reducer network, or divide the network into separate experts. Again, you can do some mathematics to count out each linear layers, and you can see that why it's turning out to be true. It's an exercise for you. So what they've done is that they divide this linear network into subsections, into sublinear layers. Okay, and each one of them is a, an expert. And we have a gated system which tells you that, okay, this expert is good for this question, for this token. Okay, how it is done, let's see. So the first thing is that we have a large linear layer. We break it up into the small linear layers. Okay, and we get the output. Yeah. So again, you can see what's written here. It's a feed forward layer. So there are other things too. So we are breaking down this linear layer into this sub experts, expert 1, expert 2, expert 3, and then we have all this, as I said, that here in this case, specific case, this is not just a linear layer, but there are also non-linearities out there. Okay, so it's the set of linear layers. So what I'm saying is that the feed-forward network is divided into this separate expert categories. Okay, and accordingly the data are chosen, and then a gated system is a gated module is selected to tell you that which is how much is important. Now there are two ways. One is the dense, where you put importance on each one of them. Probably one of them will have more, but you will actually pass through all of them. Okay, but that you may ask that why it's important. The importance is, you will understand later on. You can actually understand which expert has given what context to the entire thing. So this is nothing but a weighted average of all the outputs of the each of the experts. That is the dense MOE, where you incorporate all the like the weights. The gate tells you this is the weights. This is also learnable. Yeah, and I'm not going into much more details, but essentially each expert, the mathematics of this is written here. Linear layer, non-linear, and then a weight and bias again, 2 layers. And the dense softmax is, this GX is nothing but a softmax over a learned layer. So it's giving a probability distribution. So these are learned. Okay, these are learned. So it's learning. And um, and a sparse MO is that you only select specific one. So you, via top K selection, you select the top K ones which are giving the best results, and then build a softmax over that. Okay, so this is how, again, the rest of the things are same. This is how you can reduce the number of layers. Again, so let's take an example. Let's say for top K, you have this V. So what you do, you select the top K, and leave everything to minus infinity, and then take the softmax. So you see the softmax becomes the probability distribution over this two, because this was the top k, the top two one there. In this case, k is equal to 2. So this gate is nothing but this gi is nothing but vi if it's in the top k, minus infinity otherwise. And this is how the now all of these are made 0, only the it's passed through the second and the third export to get this. Okay, so this is the sparsely gated mixture of experts. And the reason I was the why dense expert can be helpful, or even the sparsely gated, is that you can actually understand that, let's say for this mixture's output, you can say that which part gave which, from which expert the part has come from, which expert gave which part. This can help you make it interpretable, that um, which part is important, which is the expert working this in the way you want it to. Okay, so that's what the useful of NS of expert is. And this using this also, you can actually reduce, if you want to pre-train your whole model from scratch, this can actually help you divide into sections and engineer the models and give the data set in that corresponding manner. This can really help. So I have talked about the learning resources. There's a lot of learning resources. Andre Karpathy is there, who wants to understand the foundations mathematics. Andre Karpathy built a large language model from scratch. Who want to understand on a managerial level, these two are okay. And these are the good notes. And I also built a lectures for the mathematics part. No, not so much of application, but the foundation plus parts. So you can also look into my lectures too. So this is for foundation. This is for applications, or other engineering people mostly, how the engineering thing happens. So this is all about my talk, guys. I am glad I could complete within the time frame, even if there was less time. And any questions, guys? Yeah, in terms with this course and discussion lecture.
Hi, me again, Dipanjan here. I just a quick question. So I saw you had a part about the human reinforced learning, right? And whether the model is performing, or how well it is performing. And again, there's a practical problem we face. So we have the pre-trained model. We did a CPT on it with LOI, BFT, and things like that. We got those graphs which said that, oh, look, the training has gone well. No, catastrophic forgetfulness and this and that. So none of them seem to suggest any of the parameters were off. But then again, the output was not as good as expected. Now, we could not get the time from people to actually, come out with dozens or hundreds of outputs and ask them to grade it. We just could not get the time from the experts for that. So I was wondering if there are other ways we can check whether the CPT is helping or not.
So after I've talked to you, I understood that the problem is in the data set, not in the model. The model is never the problem. Okay.
Might very well be. I don't believe the model is the problem, but how do I get the model to do what I want is my question.
It's same asking. Okay, so let me help you understand so that you can think over it. Okay, it's like, think instead of a model, think in terms of teaching a baby. Okay, so when you're thinking of teaching a baby, if you give the baby a problem it cannot solve, what do? Make it easier for it. If it cannot do it, make it easier for it, for the baby. So think your model in terms of as a baby. So if your model cannot solve a complex problem, can it solve an easier problem? And what is the minimum compute I need for that? Simple, like, so what is the simplest problem I can solve? Can it solve it? Then see that, can I increase the data set a bit? It is solving, and you have to do this experimentation proper in a scientific manner. If you just give in the data set, it will never work. That's for sure. I like
That's
that.
for sure. Just wanted to say that yes, we also have another track where we are actually trying to make it work for smaller and smaller questions. But my question was not that. I think I might not have been clear. My question is there any way that, or could you give some techniques as to how to automatically judge the output of an LLM?
Good question. Evaluating the LLM. So what so you should read. I will also send you some. So you should read how GPT and all these things do specific evaluation on specific data set of mathematics or whatever your code is. Go code specific, and you should build an evaluation, a set of evaluation metric for each one of them. Similar to Perplexity, you can build other, and you can evaluate that on the test data set or validation data set and see how it works. But again, reading the GPT paper is really helpful because they have supervised on the same thing. You should see the evaluation metrics. Does it answer your question?
Dipanjan,
Yeah.
Just asking, curious, are you trying to generate the program in one go? In one
That's a
shot?
very good question.
I mean,
let's say no. I actually work with the. So when we started off, just to give some background, we thought, oh yes, right, LLMs can do everything, so we'll generate it in one go. But I think we're at a stage now where I at least am quite sure that it will not work, and I need to refine it with the LLM exactly in the way that you mentioned. So that's there. That's fine. And this, I guess, we know. I mean, does that answer your question?
Yeah. And next question is that have you tried, breaking the problem into smaller parts and make them work in an integrated way? That's another thing you can do. In my case, I often do that.
Problem. Yes. Yeah.
Makes sense.
Okay.
So decompose that large problem statement into multiple small steps, and then at the end, sort of put them all back in together. I am trying to do that now, but I'm trying to do that now. That's exactly what I'm trying to do.
Second point, when you generate these programs,
so 1 minute, Professor Kamokar.
Yeah.
I have to leave. So
okay. Please complete your things.
No. So yeah, I mean, I have everything. I have shared my presentation. Let me know if you have any questions. I have to leave now. So feel free to DM me on LinkedIn or email me, and I would like to help you out. Okay. So all the best, guys. Bye-bye.
Thank you very much for that.
And maybe Mr. Karbukar, we can also discuss it in detail in the session during tomorrow's
we can discuss
that
tomorrow.
Be probably the best.
Yeah, that's true.
Interest of time for everyone.
Yeah.
Bye, everyone.
Bye. Thank you so much.
Thank you so much.
Thank you. Thank you so much.
Professor, you were saying something, or that's it for the day? Okay, I guess that's it for the day.
Professor Karbukar, if you want to do, let us know anything. We are eager to know. We can.
No. What I was suggesting, just to, I will take 1 minute time. Just I was suggesting if it is possible to break the problem into several pieces and phase by phase you can proceed. And if you do that, normally what happens, a coding agent, if you use a coding agent, it will create the programs into separate files and separate folders if required. It will do it for you and place them into appropriate folders, and they will work together in sync. That's how it can work. And if you use a coding agent instead of using an LLM directly, I mean, in generating the whole thing in one go, then probably your problem may you probably will be able to solve the problem, to solve it, I believe.
Professor, that's exactly what I'm doing right now. I'm in fact using Cloud Code. Let's be here. Yeah. So
okay.
And that does exactly what you are saying. I do agree with you about with what you are saying, that using an agent which can work autonomously and wake it up and work autonomously might be the way. But not just for the theoretical sake, as well as to see if I have missed anything in the training, in the validation part. My questions were for that, right? So
no, that's okay. That's okay. I mean, you are in this case, you are trying to know how you can make the model best to, produce the output, isn't it? That's fine. But agentic system development is a different kind of approach. We can discuss about that tomorrow itself, right?
Thank you very much.
Yeah. You're welcome.
Thank you.
Thank you, sir.
Thank you. So drop it. Okay.
Thank you. I think we can drop off, right?
Okay. Bye.
Yeah, thank you. Thank you
Thank
so
you.
much.
Thank you,
Bye.
everyone. Thank you.
Bye.
Yeah, thank you.
Yes.